Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 22. We've only got 2 lectures left in the semester after this one. Today, I'm going to incorporate some text from Pittman and then go through some examples, which we'll work out through by hand. But at a high level, we're going to be emphasizing how do you calculate the probability when there are 2 or more continuous random variables involved. This leads to the notion of a joint density function, which we already introduced last time, but we were almost exclusively working in the setting of a uniform distribution over some support, the support being the set of points where that density function is non-zero. We'll go ahead and play out some of the analogs between discrete probability, which we studied in the first half of the course, and continuous probability. One of those analogs is marginalization, which we sort of danced around in the last lecture. This leads naturally to the notion of independence. And we'll look at what happens when we have 2 or more random variables. I should say normally distributed random variables, which will give us an insight on where this mysterious square root of 2 pi came from when we are dealing with just the normal distribution. So 2 or more normal random variables. All right. So we already introduced this notion of the JDF where it looks like a uniform on, say, a square, or maybe a rectangle even. But what happens when the joint density function is a little more complicated? For example, you might have a random variable or a pair of random variables whose joint density function has the feature that it's all 0 here, but then it takes non-zero values in a sort of continuously arced behavior, which then carves out this beautiful surface inside of 3 dimensions, where you think of this as being the graph in Z of the function f of x, y, which is our JDF. The particular joint density surface being displayed here actually comes from an interesting topic which we haven't had time to cover in this class. This is namely the topic of order statistics. It essentially tells you, suppose you have a collection of 5 independent uniform random variables. How are the densities of the second and fourth largest uniform random variable behaving? And we get this very interesting equation that looks like 5 factorial x times y minus x times 1 minus y integrated over this range here. The basic idea is just like with discrete probability, where we have to sum numbers to find the probabilities of events, where an event is the collection of 1 or more outcomes. Here the analog is, if we want to know, let's say, the probability that x is greater than 0.25 and y is greater than 0.5, y being the 4th smallest and x being the 2nd smallest, so this being smaller than that, you end up having to define your limits of integration using x greater than 0.25, that's given by this line, x greater than 0.25, and then here, y being greater than 0.5. And so that defines the limits on x and y, but to compute the probability, we have to find the volume under this part of the surface. And to get at sort of the intuition for that, you have to understand, again, how calculus works, where we think of infinitesimal probability as sort of volume of a small box, and then total probability as being the sum over all these little small boxes. Or in this case, they look sort of tall, but again, they're sort of slicing your probability distribution. So this is all just supposed to be a remark on what do more complicated JDFs look like? And by more complicated, we mean other than uniform. If you want to make sure that your calculus skills are up to par, I encourage you to try to check that this JDF actually integrates to 1 over the domain. Everything just ends up being a polynomial, so it's not so bad, but there are a lot of terms involved and it can be a little pesky. All right, so let's get at what is the dictionary between discrete and continuous probability. In the case when we have 2 or more random variables. So again, we have this very helpful side-by-side summary, courtesy of Pittman. Now, remember, you want to think of this this statement over here, this as being the probability that x equals little x and y equals little y. That's what the JDF means. Now, when we know that x and y are independent, we then have this nice assumption, which essentially says that we can turn the and into just multiplication. But that's not always true, right? Again, if we have 2 variables which happen to be correlated in some interesting way, then we can't just multiply the probabilities. If you want to know the probability of a set, so meaning, let's say x and y ranges in a set of values, maybe I'm drawing out balls from an urn where there's several different colors. I want to count what's the probability that I have between, let's say, 2 and 5 red balls and 3 and 4 green balls. Well, that's going to carve out a region in which I need to sum over each of the individual probabilities. So just as like an example, imagine I've got my urn, which has 5 red and 5 green. Let's imagine I draw out balls, draw out, let's say, let's say I want to do 5 balls without replacement. Let x be the number of reds and y equal the number of greens. Now compute the probability that x is between 1 and 3, and let's calculate the probability that y is between 2 and 4. So here you would have to make your probability table and then look at all the entries that satisfy both those 2 conditionals, x being between 1 and 3 and y being between 2 and 4. What you'll end up seeing is something like, here's x, here's y. X is going to be between 1 and 3, and y is going to be between 2 and 4. So So 1, 2, or 3, and then 2, 3, or 4. And so what you need to do is sum up the probabilities here. And that'll give you the probability of that event, which is the event that x be between those two values and y being between those two values. Now you can think of the entry inside of that table as exactly the height of some function, like the one that we had back here. It's exactly like this right here. This is the height, is the value, height equals value of the probability table. And so then when we're computing the probability, we're just summing up the volumes of each of these little cubes. So you see here that there's absolutely no difference between discrete and continuous. It's just that now the possibilities become sort of infinitely small. But all the usual axioms still have to hold. Probability has to be greater than or equal to 0. The sum of all the probabilities is equal 1. And then important topic for today, is this marginalization, which just says if I sum along all the possible values for y, I'll obtain the probability distribution for x. So see here, to get the probability distribution for x, you sum over all y. That's sort of like eliminating y as a variable by just summing out all the y's. And then similarly for x, or determine probability distribution for y, you have to sum over all x. Now, again, the major dichotomy here is that we go from sums all the way to integrals. And that's it. If you want to know, all right, we could talk about infinitesimal probability. There's no such counterpart. It's just what's the value of this function here. Instead of it being an event, it's sort of an infinitesimal event, which is not actually an event. So we could think of this as a infinitesimal event. Dx and dy. Now, instead of summing, we now integrate. But we need everything else to still hold. We need it to be non-negative, and we need that this integral equals 1. So I'm just going to say here as a challenge, check that, 5 factorial x times y minus x times 1 minus y along the region y x less than y less than 1. Check that this integral equals 1. And you'll see that this actually is a valid PDF or not. We're going to be checking that today. Now, marginalization is exactly the analog over here. You end up just sort of integrating out y to obtain the probability density for x. And here you have to integrate out x to obtain the probability density for y. And once you've got that, you can check independence by just asking, is this formula true? So this is going to be also very important for today. And last time we got onto the topic of sort of covariance, just sort of alluding to it briefly, and we'll try to revisit that today. This is the method for computing. So how to compute the expectation of x times y. Well, you just let this be x times little x times little y, f of x, y, and then you integrate out. That is going to be the way that you compute the expectation of x times y. All right, so this is sort of the broad analog between these two subjects. Discrete probability with 2 or more random variables and continuous probability with 2 or more random variables. At times we'll actually see situations where you can have one discrete and one continuous, and then it ends up turning into sort of piecewise defined PDFs, and then you can kind of compute probability again using sums of integrals. So, all right. So let's go ahead and return to an example which we introduced in the worksheet to see how this this works. And we're going to start back in the simplest setting. So here's an example. All right, so we've got capital X, capital Y. I'm going to draw its support. In this case, we're looking at the set of points which have y greater than x, but both of those being between 0 and 1. So we have 0 less than x, less than y, less than 1. And it's going to be uniform on this. So what this means is that f of x, y, the GDF, is going to be equal to 2 for this, and then 0 otherwise. Now the question you might ask yourself is, where does 2 come from? Well, the answer here is that you need to be able to integrate from all of minus infinity to infinity, minus infinity to infinity of f of x, y must equal 1 in order for the normalization axiom to hold. Again, this right here being the normalization axiom. That summing up all the probabilities or integrating all the probabilities has to give you a total of 1. Probability can never be greater than 1 or less than 0. Now, probability density, on the other hand, can actually be greater than 1. And in fact, we see that illustrated right here. Now, how do I know this? Well, in this case, uniform probability is equal to relative area. And I know that the area of this triangle equals 1/2 height times base. Well, height times base in this case is 1. So this ends up being 1/2. Now, if I integrate the constant function 1 over a region that has area 1/2, then I'm going to only get 1/2. I need it to equal 1. So that means I need to integrate the function 2 over a region that has area 1/2 in order to get total value, the interval to be 1. All right, so let's do some follow-up calculations with this. Now, how can we marginalize? So example continued. So find the PDFs for x and y. So remember, I have to integrate out y in order to get the PDF for x. So what that means is that the PDF for x is going to be equal to the integral from y equals minus infinity to infinity of my JDF integrating with respect to y. And again, just as a reminder, this is my GDF. And for this purpose here, when we're going to be integrating out y, we want to take sort of these vertical slices. And remember, this function is going to be 0 up until this point, and then it's going to jump to value 2, and then continue back down to 0. And so then we're basically computing the area under the curve of a function that's 2, but where the limits of that integrand are changing as a function of x. So let's go ahead and figure out, well, what are the limits? Well, here you can just do a little bit of geometry. You think, all right, if this is x and this enters at y equals x, and I know that the lower limit of my integral has to be x. And then it exits the support at y equals 1. So I can now figure this out. I say, okay, well, I'm integrating from y equals little x to y equals 1, because that's the part where this JDF is non-zero, of the function value 2 dy. Now, luckily, constant functions are super easy to integrate. You just multiply it by y and then evaluate the endpoints. So this is 2 times y evaluated at y equals 1 and y equals x. And so I now get 2 minus 2x. Or I can think of this as 2 times 1 minus x. And this is valid for as long as x is between 0 and 1, and it's going to be 0 otherwise. That's our PDF. All right, great. So let's go ahead and repeat this for y, just to make sure we've got a handle for this. So now I need to imagine slicing in a slightly different way. Maybe I'll use salmon color to figure out what these limits should be. So now I'm going to hold y to be constant and let x vary. And I want x to be sort of increasing. So it's clear that this enters the support at x equals 0, and then exits the support at x equals y. So it ends up kind of being the opposite of what we had previously. So now we're in business. All right. This ends up being the integral between x equals 0, x equals y of 2. We're integrating out x, so this is a dx. And so we get the same sort of thing. It's 2 times x, now evaluated at x equals y and x equals 0. Now, when we plug in x equals 0, this expression is going to go away. So we just end up getting 2 times y as the value for my PDF. So I now have that the PDF for y looks like 2y for y between 0 and 1, and 0 otherwise. And over here, I had 2 times 1 minus x, and 0 otherwise. So if I were to just draw these graphs real quick, this kind of looks like, all right, well, at x equals 0, it's 2. All right, let me back up a little bit here. And 0 otherwise, so this is f of x. And now if I use, let's say, salmon to draw for y, still use blue, then I look like this. and then it drops back down to 0. And this ends up being f of y. So you can see how they're kind of counter indicated or counterposed to each other. Now we can use this to check independence. So question, independent? Well, first of all, the answer is no. In part because the support of f of x, y, the JDF, is not equal to the support of f of x times the support of f of y. But we can also just check using an equation because remember, based on the other slide we had here, it's independent if and only if f of x, y, the JDF, is equal to the multiplication of the PDFs. And so by checking that this right hand fails, we then know that this is not independent. To write it out a little more specifically, we know that 2 is not equal to 2 times 1 minus x times 2 times y for all x and y. In particular, if we were to plug in x is equal to a half and y is equal to 3/4, we would get that 2 times 1 minus a half, and then take 2 times, let's say, 3/4. And what would that give us? All right, well, a half times 2 is going to be 1, and then we end up getting 3 halves. And again, notice that this is a probability density that is greater than 1. But if I restrict to actually integrate any little ball, it's going to end up being, well, roughly the area of the base, which is small, times the number, which can be big, but the resulting volume is still going to be less than 1. All right, so that proves that these things are not independent. So let's go ahead and play around with this notion of covariance of x and y. There's a question. So what is the covariance of x and y? Well, here it's worth remarking that covariance of x and y is going to be equal to 0 if and only if x and y are independent. So we already know this thing's not 0, but now the question is, what is it? Well, let's go ahead and work out some more general math here. So remember that the covariance of x and y is equal to the variance of, or sorry, it's the expectation of x minus the mean of x times y minus the mean of y. Now the reason why we study covariance is because we want to see actually if certain values tend to be correlated. So here is a quick example where, imagine I've got some data points. Where I'm looking here at possible values for x comma y. But I can see that if I compute, let's say, the average of all the x values and I compute the average of all the y values, I get something like each of those being roughly 0, assuming I've got enough points down here. And again, the x values just being imagine if I project each of these points down to the x-axis, and then the y values being, I project each of these points down to the y value. And I could just study these as distributions in one parameter. Now, notice this has the property that when an x value tends to be larger than 0, the y value also tends to be larger than 0. And you can see that if I look at that point right there, it's the same thing as going up this way. And you can see that this number times this number, which are both positive, results in a positive. So these are points here where these are x comma y I such that x minus e of x times y minus e of y is greater than 0. And actually the same thing is true down here, except now I've got, let's say, a point where it's negative, so it's less than the expected value for x, but its y value is also less than 0, which is less than the expected value for y. So if I take a negative number times a negative number, then I get, again, a point where x minus expectation of x times y minus expectation of y is greater than 0. And so far, this is right now the lone point, it looks like. Is less than 0, because I have something whose y value is positive, but whose x value is negative. And so the bottom line is if you then sum up these multiplications, you weight it by how probable is that value. Well, in this case, using empirical distribution, we say every point is equally probable. Then this is a situation in which expectation is, expectation or covariance, I should say, is greater than 0. So is greater than 0. But if I had a situation where, let's say my points looked a little more like this. Well, this is a situation where covariance should be approximately equal to 0. So this implies it's uncorrelated data. But anyhow, let's go ahead and figure out how to compute this covariance. And so I'm going to take this expression and weave it on through. All right, well, let's go ahead and multiply things out. So we know that we have the expectation of x times y minus x times mu y minus mu x times y plus mu x times mu y. Now, by linearity of expectation, this ends up equaling expectation of x times y minus mu x mu y. Let me maybe go a little bit slower here. So minus mu y times the expectation of x minus mu x times the expectation of y. And then these are just constants over here. So when I compute the expectation, I just get the number back. So this is plus mu x mu y. And so if I figure this out a little bit more, so this is mu y mu x. This is minus mu x mu y plus mu x mu y. Okay, maybe these cancel. but I still have one of these factors left over. So this ends up equaling the expectation of x, y, minus, maybe to make it more suggestive, expectation of x times expectation of y. And so this ends up being our covariance. So this just shows you why we would compute this quantity, this expectation of x times y, because it's one of the critical ingredients for computing this covariance. All right, so let's go ahead and try it. So returning to the example. So now I need to integrate x times y against this function, f of x, y, little x, little y, dx dy. And this is going to be the expectation of x and y in this case. So, well, luckily, this is just 2. F of x, y is just 2. So I can just bring that out and now focus on getting my limits right. Well, if I'm integrating out x first and then y, I mean, a couple ways of approaching it, but let's do it this way. So if I'm fixing y and letting x vary, so I'm fixing x, or fixing y and let x vary. And you can see again that this goes from x equals 0 to x equals y. And then I'm going to eventually integrate with respect to y. All right, so, and those limits are going to be from y equals 0 to y equals 1, but my x limits are from x equals 0 to x equals y of dx dy. All right, well, here we're essentially integrating 1, which is just going to give me x, evaluate x at the endpoints. It's just going to give me y. So now I have 2 times y dy, integral from y equals 0 to y equals 1. And notice I've already got the 2 there, so this is just ends up being y squared. And then evaluating at 1 and 0. But my apologies, I made a mistake here. I forgot to include our integrand, which is x times y in this case. There I was just checking that this actually integrated out to 1, which it does, obviously. So here I have x times y, dx dy. First I have to integrate with respect to x, so that's going to give me x squared over 2 times y. I need to evaluate at x equals y and x equals 0. And then I've got also y equals 0 to y equals 1 dy. X is equal to y, so that gives me, now I've got y cubed over 2 inside. So now I have to integrate from 0 to 1 of y cubed over 2 dy. And again, I can't forget my 2 that's floating about here. So I've got 2. 2's are going to now cancel, so now I get y to the 4th over 4. From 1 to 0. So I end up getting a 4th. Now, what was e of x and e of y? Well, now I just need to use the PDFs that I derived over here to compute the expectation of x and the expectation of y. So let's go ahead and do that real quick. So expectation of x is going to be the integral from 0 to 1 of x times f of x dx. This then, if you recall, was the integral from 0 to 1 of x times 2 times 1 minus x dx. And so multiplying everything through, we end up getting 2x minus 2x squared. Assuming I didn't mess anything else up. Integrate from 0 to 1. Well, luckily this ends up equaling x squared. And this is going to be minus 2x cubed over 3. Plug in 1 and 0. 0 doesn't matter, so I just plug in 1. So this is 1 minus 2/3 equals 1/3. So that's the expectation of x. And just in the interest of time, I'll let you run through for yourself what this is. And you'll see that it should be 2/3. So this implies that the covariance of x and y, which is going to tell you just how correlated x and y are as random variables, is, well, remember, expectation of x times y minus the expectation of x times the expectation of y, which should work out to be, well, what do we got here? 1/4 minus 1/3 times 2/3. So that's 2/9. Let's make this all over 36. So 9 over 36 minus 4/8 over 36. That's right, 9 times 4, good, yep. Goes 1 over 36. So there's actually some positive correlation between x and y when we know that the joint density function looks like this upper triangle. All right, we'll do some more examples of this in class, but I think probably the more important thing here is to go ahead and move on to our next topic, which is how do we treat independent normal random variables? And let's look at that special case because the integration can be a little hairy. And part of the purpose of this part of the course is to go through and sort of demonstrate some of that. All right, so what I'm going to say is maybe sort of homework. Let's look at if x is exponentially distributed according to some lambda and y is exponentially distributed according to some parameter mu. Let's calculate the probability that x is greater than y. Now, what that means is that when I define my joint density function and I take this pointwise product, and again, I should say that these are independent. Then how do we compute this probability? Well, what ends up happening is I need to carve out this region here where x is greater than y. And you can integrate this in various ways, but I recommend fixing y and then integrating over slices that look like this. And that should tell you, so this, the volume under f of xy, which is going to look like lambda times mu e to the minus lambda x minus mu y for this area, that right there is going to equal the probability that x is greater than y. All right, and we'll do this calculation in a live session soon. All right, let's push this now into normal random variables. And we're getting now at the question of where does that funky square root of 2 pi come from when you deal with normal random variables. So let's, my heading's been so far. Yeah, I'll use blues here. So now let's look at, so independent variables. So what this means is that, you know, I've got, let's say, x is distributed according to this, and then I look at y, and it's distributed maybe with a different kind of variance, y. So here I've got x, let's say, is normally distributed with mean mu x and variance sigma x squared. And I've got y, which is normally distributed about mu y and sigma y squared. How do they vary jointly? And let's assume they're independent. So what you need to imagine is that if they're independent, I'm now multiplying each sort of value here, and I'm using that to scale this entire curve. So if I do that, if I try to scale that much, you'll see that I'll get a little bit of a reduction so that this ends up being the result of that multiplication. Whereas if I'm like, let's say over here, and I'm multiplying this by this curve, then I should get a larger value, something like that. And so as you trace along this in the x direction, you're going to get this family of normal distributions that kind of go up and then come down. Altogether, it looks something like this. And so maybe I should just go ahead and lasso this and then I will incorporate this into my notebook here. So this, what I'm drawing here now, is the result of multiplying f of x little x times f of y little y, which is going to be my JDF because I'm assuming x and y are independent. All right, so now let's try to figure out some properties of this distribution. Now, one thing we already know is that if I slice at a constant value of y, then I'll get some area, and that area actually ends up being this height here. So let's operate under the assumption where mu x is equal to mu y, which is equal to 0. Now let's assume further that our variances for both of these are 1. So these are both unit normals. So i.e. both unit normal distributions. So how do we figure out what the value of this is when we slice it, let's say at y equals 0? It should be the total area under the curve of this multiplication. This ends up leading you to the question that's sort of been in the back of our mind, which is what is the integral from minus infinity to infinity of e to the minus x squared, say over 2. dx. Now, I claim that approaching this directly is impossible. Is impossible. The reason for that is essentially because e to the minus x squared has no elementary antiderivative. And by elementary, that actually has a precise meaning in math. It's expressible using sort of polynomials and sines and cosines and things like that. But it turns out we can still find out what this number is, but by doing sort of a magical trick, which involves actually not computing exactly what this integral is, but by computing its value squared. And so that's kind of the weird trick here. So how do we figure out what this value is squared? Let's do a little bit of algebra here. So here's our trick. Well, we can compute actually the value of this integral e to the minus x squared over 2, let's say, dx squared. So where this factor right here is the magic trick. Okay. Now, why is this the magic trick? Well, I'm going to just write out what does it mean to square this in a slightly different language. So suppose I just write the same expression by itself. But now I'm going to recognize that because I'm integrating out whatever the variable is, it doesn't matter what I choose. So let me just go ahead and use a different variable. Let me call this the same thing as y squared over 2. And then I end up getting this, which is that this ends up being the same thing as the double integral from minus infinity to infinity of e to the minus x squared over 2 times e to the minus y squared over 2 dx dy. Now I can add those exponents. And so what I end up getting is e to the minus x squared plus y squared all over 2 dx dy. And I'm integrating over the entire plane. Now, remember, I can always switch to a different coordinate system. Instead of using Cartesian coordinates, which measures up and down and side to side, I can use polar coordinates, which measures angles and radial displacement. So now I'm going to use, and here's where the other magic trick comes in. Let's go from Cartesian to polar. And so what we end up getting is now, I could call this from 0 to infinity of r dr d theta, where our volume element here has now changed from dx dy to r dr d theta. But I now need to take any time where I see x and y and replace it to something that uses uses r and theta. But remember, we know that r squared, x squared plus y squared equals r squared. And luckily I've got x squared plus y squared in my integrand. And so I can now do this. So I get e to the minus r squared over 2. And then I have my r dr d theta. And although things don't look better, there's an important thing here that saves it, which is that I've got an r outside of this integrand, which allows me to now evaluate this integral. All right, so let's just test. Remember, try. So what is ddr of e to the minus r squared over 2? Well, it's going to be e to the minus r squared over 2 times ddr of minus r squared over 2. And so this expression here ends up being minus 2r over 2, which ends up canceling out our 2 and giving us just our minus sign here. So actually we can already recognize that this is equal to this, the derivative of this expression, up to a minus sign, right? So we just get that. Now we have this as minus r e to the minus r squared over 2. So we're in business. We can now actually integrate this expression because we now have that little r, which came only because we worked in 2 dimensions and we switched to polar coordinates. That's sort of one of those mental gymnastics that we should always be a little impressed and mesmerized by. So we now can finish this. All right, well, if we're integrating with respect to r, we're actually done. And notice theta doesn't really matter here. So we have 2 pi, and we have minus e to the minus r squared over 2 evaluated at infinity and 0. But when we plug in infinity to the e to the minus something, that's going to go to 0. And then we plug in 0, we get 1. And so actually the value of this integral, let me just go ahead and summarize everything I was trying to say. This squared is actually equal to 2 pi. And so the implication is that the integral under the area under the curve for this, when it's not squared, is the square root of 2 pi. And so that's actually exactly the thing that we put in the denominator, make sure that this all normalizes out appropriately. So there's a couple things we've learned from this. which is that if we, so here's some takeaways. If X and Y are independent unit normals, then the JDF of X and Y is 1 over 2 pi e to the minus x squared plus y squared over 2. Which is exactly what would happen if you took the formulas we used earlier with that pesky square root of 2 pi and multiply them together. Square root of 2 pi times square root of 2 pi gives you 2 pi. So that's pretty cool. Some other things that we can sort of benefit from by understanding this a little bit better, which is when we switch to r and theta, we actually get another way of thinking about this JDF. So in polar coordinates, now we've got something like f of r theta, little r little theta. This ends up equaling something like 1 over 2 pi e to the minus r squared over 2. Now the question is, what does this work out to be when we want to go ahead and compute the, let's say, marginalize, but now with respect to r? So if we marginalize with respect to r, we now get something like this. So let's marginalize with respect to r. So what does that mean? That means I need to compute f of r, little r. That's going to be the integral with respect to theta of this expression. R dr d theta. Oops. D theta, but we're going to imagine that we're holding r constant. So because r is constant. And so now just by integrating out by theta, we end up something like this. We end up getting, well, the 2 pi goes away. And so we end up with r e to the minus r squared over 2 for r greater than or equal to 0 and 0 otherwise. And that is our marginal for 2 normally distributed random variables. And remarkably, this has a very beautiful graph. In particular, at r equals 0, it does actually equal 0. But then it kind of goes up and then down, and then there's this long tail. So this is the PDF for r. Minus r squared. And so in particular, if you look at probability density for how radius varies, there ends up being some sort of maximum value roughly around r equals 1, at least in the case where we're looking at this. And this right here is actually called something special. This is the Rayleigh distribution. For r. All right, so that's it for today. I look forward to seeing you in class soon.